The word uranium carries weight long before you even understand it. It sits quietly in the background of some of the most defining moments in human history, shaping the modern world in ways most people never stop to examine. It powers cities without smoke. It reshaped global warfare in a single flash, and it continues to test how far humanity can go with knowledge before consequences catch up. If you're here for real understanding, not surface-level facts, you're in the right place. And if this kind of deep dive into the unseen forces behind everyday reality is your thing, make sure you're locked in with the channel, because this is where the ordinary gets decoded. Uranium is not just powerful in the way people casually use that word. It is powerful in a literal, measurable, physical sense that no chemical fuel can match. To understand why, you have to move past the headlines and look directly at what makes this element fundamentally different from everything else we use for energy. Understanding why uranium's atomic structure makes it uniquely powerful. Uranium sits near the bottom of the periodic table with an atomic number of 92. That number is not just a label. It means every uranium atom contains 92 protons in its nucleus. What matters even more is that this nucleus is large, heavy, and unstable. That instability is the starting point of its power. Unlike lighter elements, uranium's nucleus does not hold itself together as tightly. There is, a delicate balance between the forces pulling it inward and the forces pushing it apart. When that balance is disturbed, the nucleus can split. That process, known as nuclear fission, is where uranium separates itself from every other energy source humanity has ever used. When a uranium-235 nucleus absorbs a neutron, it becomes unstable and splits into smaller atoms. In that moment, it releases additional neutrons along with an enormous burst of energy. Those neutrons go on to split more uranium atoms, creating a chain reaction. This is not combustion. Nothing is being burned. Instead, mass itself is being converted into energy. According to Einstein's mass-energy equivalence principle, even a tiny amount of mass can be transformed into a massive amount of energy. This is why uranium stands alone. The energy released from splitting atoms is, really, millions of times greater than the energy released from chemical reactions like burning coal or oil. The difference between uranium-238 and uranium-235, well, it really explains everything. Natural uranium is not uniform, you see. It consists mostly of uranium-238, which makes up over 99% of what is found in nature. The remaining fraction, less than 1%, is uranium-235. That small percentage, honestly, is what gives uranium its extraordinary value. Uranium-235 is fissile, meaning it can sustain a chain reaction. Uranium-238, on the other hand, is not directly fissile under normal conditions. This distinction is critical. Without uranium-235, nuclear reactors and atomic weapons would not function the way they do. Scientific literature from organizations like the International Atomic Energy Agency consistently emphasizes that the rarity of uranium-235 is what drives enrichment processes. Enrichment increases the concentration of uranium-235, allowing controlled reactions in power plants or, at much higher concentrations, explosive reactions in weapons. This imbalance, where the most useful isotope is also the rarest, is part of what makes uranium both powerful and strategically important. It is not just about having uranium, it is about having the right kind. Why does nuclear fission release energy on an unmatched scale? Well, in traditional fuels, energy is released by rearranging electrons in chemical bonds. These reactions, you see, operate on a relatively small energy scale, but nuclear reactions, on the other hand, operate on the nucleus itself, which is honestly orders of magnitude more energetic. There's a widely cited comparison from the World Nuclear Association that explains a single uranium fuel pellet, which is about the size of a fingertip, can actually produce as much energy as a ton of coal. And this is not just theoretical, it's based on real reactor output data. This kind of energy density really changes everything. It means less fuel is needed, less material is transported, and well, less waste is produced in terms of volume compared to fossil fuels. However, the trade-off is that the waste produced is radioactive and remains hazardous for extremely long periods. And this is where uranium's power becomes, a bit complicated. It's not just about how much energy it can produce, but also about how long its effects last. The discovery of radioactivity really changed how uranium was understood. For decades after its discovery in 1789 by Martin Heinrich Klaproth, uranium was treated as little more than a curiosity. It was used to color glass and ceramics, producing a distinctive glow that, fascinated people at the time. Everything changed in 1896 when Henri Becquerel discovered that uranium emitted invisible radiation. This discovery was not intentional. It actually came from experiments with photographic plates that revealed uranium's ability to release energy spontaneously. The work of Marie and Pierre Curie expanded on this, establishing the field of radioactivity. Uranium was no longer just a heavy metal, it was a gateway into understanding atomic energy. Historical accounts from scientific journals of the early 20th century described this shift as one of the most significant turning points in physics. Uranium became a subject of intense study because it hinted at energy sources far beyond what was previously imagined. The role of uranium in nuclear energy really reveals its constructive power. Uranium's most widely known peaceful application is in nuclear power generation. In a nuclear reactor, uranium fuel is arranged in rods. When controlled fission occurs, it produces heat. That heat is then used to convert water into steam, which drives turbines and ultimately generates electricity. Unlike fossil fuel plants, nuclear reactors do not rely on combustion. This means they do not emit carbon dioxide during operation. Reports from the Intergovernmental Panel on Climate Change consistently list nuclear energy as one of the lowest carbon energy sources available. This places uranium right at the center of modern discussions about energy transition. Countries looking to reduce emissions often consider nuclear energy as part of their strategy. However, the benefits come with challenges. Nuclear waste remains radioactive for thousands of years, requiring secure storage solutions. Accidents, though rare, have long-lasting consequences, as seen in historical events like Chernobyl and Fukushima. Uranium's power in this context is both an advantage and a responsibility. The Manhattan Project revealed uranium's destructive potential. During World War II, uranium became the focus of one of the most secretive scientific efforts in history, the Manhattan Project. Scientists discovered that by enriching uranium-235 to high levels, they could create an uncontrolled chain reaction. The result was the atomic bomb known as Little Boy, which was dropped on Hiroshima in 1945. It marked the first time nuclear energy was used as a weapon. Declassified documents and historical analyses from institutions like the United States Department of Energy described the event as a turning point that really redefined warfare. The destructive power released in seconds demonstrated what happens when uranium's energy is unleashed without restraint. This moment cemented uranium's reputation as the most powerful element, not just in theory, but in practice. Uranium's density gives it, some pretty unique physical applications beyond just energy. Uranium is not only powerful because of its nuclear properties, it is also, honestly, one of the densest naturally occurring elements. This density makes it useful in applications where mass and strength are absolutely critical. Depleted uranium, which remains after enrichment, is used in armor-piercing ammunition and military armor. Its ability to penetrate targets comes from its weight and structural properties. Studies published in defense and materials science journals note that depleted uranium can self-sharpen during impact, increasing its effectiveness. This has led to ongoing debates about its use, particularly regarding environmental and health effects. Again, uranium's power extends beyond energy into the physical realm. Mining uranium shows how deeply it is embedded in the Earth. Uranium is found in the Earth's crust, often in minerals such as uraninite. Major deposits exist in countries like Canada, Australia, Kazakhstan, and Namibia. The extraction process involves mining the ore and processing it into a concentrated form known as yellowcake. From there, it is refined and prepared for use in reactors or further enrichment. Reports from organizations like the World Nuclear Association highlight the complexity of uranium mining. It requires strict environmental controls to prevent contamination of water sources and exposure to radiation. This process underscores another aspect of uranium's power. It is not easily obtained or handled. Every stage requires precision and caution. Health and safety concerns highlight uranium's long-term impact. Natural uranium is only weakly radioactive, but its decay products can pose serious health risks. Exposure to uranium dust or prolonged radiation can damage tissues and increase the risk of cancer. Regulatory bodies such as the World Health Organization emphasize that the primary risk from uranium is chemical toxicity, particularly to the kidneys. However, in high concentrations or in nuclear accidents, radiation becomes the dominant concern. This dual nature, chemical and radiological, adds another layer to uranium's complexity. Its effects are not always immediate. They can unfold over years or decades, making its management one of the most challenging aspects of modern science. Uranium's role in global politics proves its influence goes beyond science. Uranium is not just a scientific element, it is a geopolitical asset. Control over uranium resources and enrichment technology has shaped international relations for decades. Countries with nuclear capabilities often rely on uranium for both energy and defense. This creates a balance of power that extends far beyond economics. Treaties such as the Nuclear Non-Proliferation Treaty aim to limit the spread of nuclear weapons while allowing peaceful use of nuclear energy. Uranium sits at the center of this balance. Policy papers from global think tanks consistently describe uranium as one of the most strategically important materials in the world. Uranium forces humanity to confront the limits of its own progress. Uranium represents a paradox. It offers a solution to energy demands while posing risks that span generations. It can power cities or destroy them. It embodies both advancement and caution. Scientific and historical literature repeatedly returns to this duality. Uranium is not inherently good or bad. Its impact depends entirely on how it is used. This is why it is often described as the most powerful element on Earth, not just because of the energy it releases, but because of the consequences tied to that energy. It forces decisions that cannot be undone easily. It requires responsibility on a scale that few other technologies demand. Closing thoughts bring everything back to what matters. Uranium's story is not finished. It continues to evolve as new technologies emerge and global priorities shift. Whether it becomes a cornerstone of clean energy or remains a symbol of caution depends on choices being made right now. If you've made it this far, you're not just watching content, you're building understanding. That's the whole point of this channel. Share this with someone who takes knowledge seriously and make sure you're subscribed so you don't miss what comes next.